job just because the camera in here does not work. 1 second.
I can see you, Bart. I can see you and hear you loud and clear.
Right. I'm on 2 different monitors, so I'm going to have to share my screen on a separate one, which is the one I'm looking at. And one, and share window. Oh, no, that was the wrong one. Stop sharing. There we go. Can we see the screen? Oh, yes. I can see it on mine down here. There we go. So, yes, the title of my talk, yes, batteries of the future, kind of what. So the work I do here is I work in the Bruce Group here in the Materials Department at Oxford. I'm also a member of Trinity College, and I'm doing a PhD, which is kind of a talk program which you do after university degree if you want to, a talk program, a research program. And my research is looking at batteries, and specifically solid state batteries, which hopefully by the end of the talk you'll be able to have an understanding of A, what they are, and B, kind of what they promise for the future. So just to first give a kind of summary of who am I as a person. So let's move this. Where's the option for a laser pointer? I don't have a laser pointer. Okay, that's fine. So yes, just a timeline of who I am as a person and how I got where I am now. I was born in 1999 in the West Midlands, and I did all the usual things of going to school, going to secondary school, and doing my GCSEs. I did them in around 2015, and then ran about. This is where you guys are now, in the 15 to 17, 15 to 18-year-old kind of category. I did my A levels. I did maths, physics, and chemistry because they were the ones I enjoyed the most at GCSE, and I did those for my A levels. And I went to do chemistry at Warwick. I got 3 A's with my A levels. I went to do chemistry at Warwick in 2017, and I enjoyed the course I did at Warwick was an MChem, where you do a small research project. And if you do courses in the sciences, you'll see this offered for a lot of courses, and I would recommend doing it. I certainly enjoyed it, and because I enjoyed it, I applied for a PhD, which is where I am now, doing a PhD, or a DPhil, as we call it here, at Trinity College, which I started 18 months ago, around about just over 18 months ago. So as I said, the work and the group I'm in is on batteries. In recent years, they've become, what's the correct word? There's more notoriety around batteries, especially because of the Nobel Prize in 2019, so just under 4 years ago, for these 3 gentlemen, Stanley Whittingham, John B. Goodenough, and Akira Yoshino. And my aim of some of the stuff I'm going to go through is that you're going to understand why this gentleman and this gentleman, John Goodenough and Akira Yoshino, both got their Nobel Prizes for batteries, which I think is very deserved considering how much we utilize batteries today. So just to summarize, why do we need batteries? Well, batteries are a type of energy storage. And why is now there been such a push for energy storage in this modern world? Well, it starts off with, on a national grid level, with us burning gas, oil, and coal for our electricity usage, which is very polluting and leads to climate change, and then also very non-renewable. We can't make fossil fuels, and they're a finite resource. So we need to look at more renewable sources of gaining energy, and what types. So Rich has got a Slido, I believe, for me, asking what types of energy sources do you think there are which we could use, which are renewable?
If I could just interrupt here as well to say to students who weren't here earlier when I mentioned this, Slido works by, you just go to slido.com or slide.do, and it asks you for an event code, and you pop in TBC6 in that event code, and you'll come to our event. At any time today, you can ask questions for Bart, which I will put to him afterwards. And you can also take part in polls. I can see somebody has just cast a vote there. And the first poll that Bart's put in today is, what types of renewable energy sources are there? Sorry to interrupt, Bart. Back to you.
Oh, that's okay. So yeah, this is, methods are we looking for now, which will replace these sort of archaic ways of generating electricity on the left-hand side. There we go. I can see solar and geothermal as some answers. Are there any more? Hydropower, yes. Oh, I've given you a sneak peek. Am I still sharing my screen, Richard, or have you?
I've just jumped in to share these answers, and then I'm going to come off, so it'll go back to your screen, Bart. Yeah.
Yeah.
We're just letting everybody see what's coming through here. So there's a fourth one, wind. Right, I'll bring this off now. Back to you.
So yeah, that's. Shall I reconnect it to sharing my screen? Yeah, sorry. Share window. There we go. So yes, based on what people sent in, they are some of the exact ones which I also had. There we go. Where, yeah, I definitely saw mentioned were wind, solar, hydropower, geothermal. I can't remember if I saw nuclear, and then this one here represents tidal power. But the thing is with some of these methods are that some of them are, I'm going to split them into two groups, where these ones on the left are much more consistent. So a geothermal power plant will constantly be heating your water, which you can use to generate power. Your nuclear power plant will constantly be heating water to generate electrical power. And then rivers will still flow for certain hydroelectric dams. They will still flow, so you'll have constant power. Whereas with these ones on the right-hand side, it's more split into intermittent energy sources. So you can only get electricity when the sun is shining, when the wind's blowing, or when the tides are changing. So that's one reason we need energy storage, is so that we can kind of pick up the demand when these three methods, say on the right-hand side, can't supply us power because it's nighttime or something. We can use them during the daytime or during when it's windy to power forms of energy storage, which we can then use at another period in time. And then the next one is at an automotive level, which is the one which, especially the batteries I work on, lithium batteries, are most primed to replace. And this is, instead of going with a combustion engine car where it's polluting a non-fuel, much the same as the power stations above, we instead look towards using electric vehicles. Now, just at the beginning here, I want to put it to you as a question. What limitations do you think are the limitations of lithium-ion batteries for electric vehicles? Again, just as another Slido, and I'm going to come back to this one at the end when I can kind of see what people have submitted, and then I can explain, like, maybe this is how we could improve batteries for the future and what research is actually doing.
Okay, again, I'll just project that if that doesn't get in the way of your presenting, Bart, and then I'll come back to you.
Yes. Yes, that's definitely the most obvious one, which I constantly see mentioned.
Would can I put one in? Am I allowed?
Yeah. Yes, you're definitely allowed, Richard.
Is this, would a charging network come in here, or really that's more about supply or the types of batteries that people are having charged, or no?
A charging network's definitely one, but it's something which is to be addressed more in policy standpoint via governments and industry rather than something I can do for research. Yes, yeah. Polluting is another one. Polluting for many, many reasons, actually. And the last one, which I can think of, unless somebody has any extra ones, is slow charging rates, which I know are a big issue, where a current Tesla car takes almost 6 hours to charge from, I'm just going to note these down, 6 hours to charge from completely flat to completely full. And I'm just going to give you, through the rest of my talk, it will give you kind of an idea of how research is thinking of improving on these kind of areas. So first and foremost is, how can we store energy? So whipping up another Slido again, sorry, Richard. So we can't destroy energy, we can't create energy, but we can transfer it from one medium to another. So for us to store energy, we must know what are the possible energy types that we can have, different mediums of energy. So then we can select from that what we think we can use as ways of storing it. So for the next Slido is kind of, what types of energy or energy media do you know based on what you've been taught in school? I've really put them back to back here, Richard. I apologize. I realize there's a lot of these in a few slides, and then it will be a lot calmer for a while.
I'll just share what we've got coming through here.
I can see, yeah. And this is just any type of energy that you know. It's not necessarily ones that you can store, that you think you can use for storage. Well, that comes next. So to give you a little way of thinking, for the next slide we're going to do, almost immediately after this one, is kind of, what ways do you think that you can store it? But for this one, it's just any energy medium.
Can you see those 6 there, Bart?
Yeah, I can see them, yeah. So if I share my screen, I've got a long list of them, but yes, they definitely include electrical, chemical, yeah, light, thermal, sound, kinetic, and heat, yeah. So I will just go back and share my screen. So yeah, heat, I definitely saw that one mentioned. Chemical was another one. Light, these were all mentioned. Gravitational or gravitational potential energy, I don't think was mentioned. And this is a potential energy, same as kind of chemical potential energy as well, technically. Sound, nuclear, magnetic, elastic. And then lastly, electrical energy, or kind of like a voltage. And then from this, as I mentioned, we got the next Slido almost immediately after, which is kind of, which ways do you think of these energies which I've given you, which ones of these do you think we can use for a type of storage? And what I mean by this is it can retain all the energy that you've given it, and then when you can park it there, and when you come back later to you can harvest almost all of the energy back and convert it into the medium which you want, which almost always is electrical energy, because that's what the modern world runs on. So which ones of these can we store energy as for a long period of time and then reconvert it back to electrical energy?
I'll just put our screen up as well. Had the first question come through as well, so just do, if you at any point
have any questions,
question
feel
for
free
later.
to ask.
Yeah, stick them in the Q&A thread, and I will see them. I'm looking at them as they come through for Bart, and I'll put them to him at the end of the session. So there you go, Bart. Electrical, chemical.
Wave. I'd say like 5 to 10 more seconds, and then just because I'm conscious of time, because I maybe have quite a few slides left.
Yeah. Okay, back to you.
So yeah, electrical and chemical, which are kind of, chemical is is the focus of this talk. It's more looking at chemical methods of storage, but We can see my screen. Yes. So yeah, energy types for storage. As a chemical, we saw written down there. I've got gravitational potential energy is one, elastic or elastic potential energy is another, and then electrical, which we saw written down on the Slido, and then lastly heat. This is quite a controversial one. There is a heat battery which exists somewhere, I think, in either Australia or the Sahara Desert, but it seems counterintuitive, but it can work. You could do your own research if you want to read into that one. But I'll go through these top three, which I've written here, and I've split it kind of. The top one is a chemical, and these next two, so gravitation and elastic, I call kind of mechanical ways of storing energy. So looking at these two here is like gravitational potential energy, where you've got, say, a ball of mass m, and then you want to lift it up. If it's a weight, or for example, you've got to put energy in to kind of lift it up to a next weight and put it on a shelf. And that distance you've lifted is h. So the energy that you've put into the system to lift it that high is E equals mgh, where m is the mass of the weight, g is the gravitational force, or gravitational acceleration, which is 9.81, and height, the height that you've lifted it. And then the next one, and then obviously if you were to remove the shelf, it would convert that potential energy all into kinetic energy until it hits the ground. So you'd extract all of that energy left as kinetic energy, which is how hydroelectric dams work. Because your water, if you've got one where they pump water all the way up and store it there and they let it go, the mass of the water will fall, causing kinetic energy, which turns turbines and generates electricity. And this one on the right here is elastic potential energy, which I like this one because it's the kind of pull cars which you have when you're younger, where you pull a car back and you give it elastic potential energy and you let go, and then it reconverts all of that energy that you've put into straining or lengthening the elastic inside, and it converts it all the way back into kinetic energy, where the equation is a half times the spring constant times the length of extension squared, or the strain squared. But the one I really want to focus on specifically is the gravitational potential energy, because I'm going to use this to introduce the concept of a potential energy landscape. So what we have here is I've got a scenario where I've got this ball starting on the shelf, and if I push it, I roll it off, and then it falls. It plots this as its gravitational potential energy, where the y-axis is, or the x-axis is how far I push it to the right, and then the y-axis is its potential energy, or you can think of it as its height, because height is proportional to the gravitational potential energy. And what this is showing is just, it's basically a plot of the height as I roll it off of the shelf. But it's important to think of it in this kind of way, that it's actually representing the energy, potential energy that you have, in the same way that if you climb up a mountain, that is technically a plot of your potential energy against x if you walk in a straight line, because you're putting energy in to walk upwards. Because this will make the concept of thinking of a chemical potential energy, which I have on the next slide, a lot easier. So stuff which is higher in energy is the same as it being higher up, literally, as in if you've lifted it onto a shelf. So a typical chemical reaction we have here on the left, where you see the chemical potential, or the chemical energy, or the potential energy landscape, with a reaction coordinate, where you have the reagents and on the left, and the products, the more stable products at the bottom. Most chemical reactions will have what's called an activation energy. This is where you have to put energy in to break the bonds which are already within the system. So for the example of, say, fossil fuels on the right-hand side, if you've got something which is a carbon bonded to a carbon, and you want to break it down to a CO2, you have to break the carbon-carbon bond first, and that's the energy you put in. And then what you have here, the delta H, your change in enthalpy, and this is the energy you get out from the reaction. So the difference between the reagents potential energy and the product's potential energy. Now for fossil fuels, this is 48 kilojoules per mole. And this is what we use, is it releases the energy as heat, and it uses that heat and the products being gaseous, and that requires the expansion in a combustion engine, which is very, very inefficient, which is why we're moving away from fossil fuels as well. And then another example I've given is thermite, where aluminium is more reactive from the reactivity series compared to iron oxide. So when you put enough energy in to kind of poke over this maximum, you'll try and create aluminium oxide and iron. And the energy difference here is 850 kilojoules per mole. And I've given a difference as a voltage here, and this will kind of, for comparison, that will make sense later. So this is, if you were to connect up this experiment to a circuit, each electron released from this, if it was to do work, would do, as in do electrical work, so power your phone, would provide you 2.94 volts. So both these methods, or these examples I've given, show that energy released is heat, which isn't very useful for us in this world, because we want to do things like power our phones, power our electric vehicles, etc. So we've got to look at another way of storing it, or a way of harnessing energy, which is electrochemically or electrically from. So we're storing the energy chemically, but we're harvesting it and converting it into electrical energy rather than heat energy. And this is the prime example of a electrochemical cell, which, from what I remember, is taught at A level, where you've got zinc metal and copper metal suspended in their systems of their own electrolyte, and it's connected up to a electrical circuit and an ionic circuit where the salt ions can move through the salt bridge, and a reaction will occur. And I've got as the next Slido, which way do you think the reaction will go? Do you think it will create more copper metal, or it will create more zinc metal, based on the reactivity series, which you should know? Richard, are you?
Just give me one moment with that, please, Bart. If you could just, I'll be with you in 30 seconds. I'm just having problems getting it up, so I'm going to have to go back in.
Okay, yeah. So, yeah, and this is the way in which we can convert chemical energy, or the differences in energies of the reagents and the products, so that enthalpy, we can convert it to electrical power. And this is actually the exact same kind of, it's very similar cell to what was the first ever battery made, which was by, I think, Francesco Volta in Italy, I think in the 17th century or 16th century, where he used copper metal, I think zinc metal, and he used vinegar or brine as the kind of salt bridge. And that was the first battery ever made, as an electrochemical battery ever made. So it seems fitting as to use as an example.
Here it comes. It's just live now.
Perfect. And we will get onto the more juicy stuff of how lithium-ion batteries work as well from this. This is kind of a launching pad for understanding.
So far we've got people saying it will form copper metal.
Yes.
Rather than zinc metal.
Mm-hmm. Yes. And that is looking at the reactivity series. Your zinc, is more reactive than your copper. So therefore, it would rather form the more stable products would be copper metal and zinc sulfate. So if we look at it, relaying it back to that potential energy landscape I gave before, your starting products are the copper sulfate in solution and the zinc metal. And your favorable products will be the copper metal and the zinc sulfate or zinc dissolved in solution. And the difference between these in energy, so between this is a redox reaction. It's another way to think of it, where your zinc is oxidized and your copper is reduced, so it's a redox. And the difference in energy between the state of the reagents and the state of the products is, we give it electrochemically, is 1.1 volts, which is not that much when in the grand scheme of things, as you'll see later. And as I'm sure you're aware with sort of the batteries which you can obtain commercially. But because these are the reagents and these are the products, what we see is that you'll have electrons moving from the zinc to the copper metal in order for the copper to be reduced, where the copper gains the electrons given by the zinc ions as they dissolve in the solution. So your electrons will move this way, and then your sulfate ions will move this way over the salt bridge. And as this is where the copper is reduced. So you've got your Cu 2+ ions or copper 2+ ions will move towards this electrode. So it's called the cathode. And here you've got your SO4 2- anions will move towards this electrode to form zinc sulfate. So this is your anode. So if we think about this image, this is basically a battery. As I said, this is the first ever battery which was made by Francesco Volta in like the 16th or 17th century. So what does a more commercial battery like we use nowadays look like? Well, it uses these two materials, one being lithium cobalt oxide, which is just lithium, rows of lithium and cobalt, rows of lithium 1+, oxide 2-, and then cobalt 3+. And we know that those are the charges on them because you've got 2 O2-, 1 lithium 1+, and so therefore for charge neutrality, your cobalt will be 3+. And this is actually in the rock salt structure. So it's the same structure as you see in table salt. It's just instead of the chloride anions, you've got oxide anions, and then you have layers of just lithium 1+, and then layers of cobalt 3+. But this is the material which John Goodenough discovered in the 1980s and why he got his Nobel Prize. And the great thing you can do with this material is you can take the lithium out. So as you take the lithium out in this material, the cobalt is redox active, and it can go from 3+ to 4+. So now you've got kind of your one redox reaction happening on one side where your cobalt is going from 3+ to 4+. So at the anode, we must somehow do something with the lithium to change it there. And what we have is graphite. And it sounds stupid, your regular old graphite, where you've got those, each carbon is bonded on a single bond to, each carbon is bonded to 3 carbons within its own layer, and then there's a larger gap or separation between each layer. But what we can do here is exactly the reverse of what we've done here, and we can actually stabilize lithium somewhat in between these layers of carbon, layers of graphite or graphene sheets. And this is almost as if it's lithium metal, so Li0. It's slightly stabilized, but it's almost as if it is. So then we get this redox reaction here. So on one side, we've got Li1+ and cobalt 3+, and then you reduce the lithium metal, reduce the lithium ions and oxidize the cobalt cations. And so then schematically, what this looks like in a real cell is you move your lithium from the cathode to the anode and it's charged, and on discharge, you move your lithium ions from the anode through to the cathode, and your electrons will move around the circuit. And if we think about that potential energy landscape, you start off in your charged state up here. So once you've charged the battery, you've got your lithium almost in its metal form, in its Li0 oxidation state. and then your cobalt 4+, and then you've got this difference in energy between these starting materials and these products here. This is when you fully discharge the cell, and what the actual energy difference here is 4 volts, which is a lot more than what we saw of anything before. So each electron which moves through this circuit is going to do 4 volts of electrical work or power to charge all the components in your circuit, which is why it's so important for kind of the modern life we live, where everything is electronic and everything is powered by electrical energy. And then to charge it, what we do is we actually apply an opposite voltage greater than 4 volts. This has done its thing where it's gone the wrong way around. So if you apply greater than 4 volts, what will happen is in this state, this will become more unstable. So you force this higher in energy, and then this will fall back down. So it will fall, this has gone the wrong way around. So it should fall this way. So therefore, this state is actually lower in energy. And that is how your battery works when you charge it, is you apply a greater than 4 volt energy difference, and it will therefore form back to the charge state. So then it will go back to this, where and that's how it's reversibly charged, where it's much more difficult to reversibly charge, the one I mentioned previously with the copper and zinc. That is how your battery works, is you increase the energy of this by more than 4 volts. And therefore, this becomes in that scenario, in that system, this becomes more stable, and it forms these as the products. And so, yeah, your electrons go around this way around the circuit. So then I asked earlier, kind of, what are the limitations of current lithium-ion batteries based on kind of these values that we had here? And the one which first came up was the low energy density. So that's meaning that each electron which goes into the circuit isn't doing as much energy per mass of the whole cell as what we need. So if we think about this potential energy landscape like a hydroelectric dam, the ways that we'd try and increase the energy or capacity that we can store, we can either increase the mass of the dam. You can't change G because that's the gravitational force of the applied by being on the Earth, and then height. So you can change M and H. M is the equivalent of changing, or mg is the equivalent of changing A and H here, which is current or amps and time. This is a stupid way of saying like capacity or like total storage, which is the same as M and G here. But you don't want that to happen because batteries are heavy. If you keep putting more and more batteries in your car, you'll get a law of diminishing returns. You're not going to get much more range because your car gets increasingly heavy. So what you want to change actually is the height, H, of your electric dam. So you get more kinetic energy out, which then converts to electrical energy. But in this case, you want to increase V, which is the voltage here. You want to increase this distance, and therefore each electron which goes into the circuit will do more work for the components. Now, one way of doing this is two ways, is either moving this further up or this further down. One method of moving this further up is to use graphite here in commercial batteries. And this is actually exactly what your iPhone battery looks like. It uses these exact materials: graphitic anode, lithium cobalt oxide cathode. But if you were to replace this with lithium metal, which is even more unstable, so you're increasing the distance of this further up, you would be able to store more energy in your battery per mass, so you increase the energy density. The issue there is with lithium metal is lithium metal reacts with this electrolyte, much in the way that when you put lithium metal in water and it goes boom and it sets on fire, lithium metal will react with this liquid electrolyte used in commercial batteries, and that will release to battery fires, much as like you've seen with the Samsung ones, I think from almost a decade ago, but you see it in electric scooter fires and certain Tesla car fires as well. And the research I do is actually replacing this liquid electrolyte with a solid electrolyte, which allows lithium ions to move through it but is electrically resistive, so electrons still go over the go through the circuit. And some of these solid electrolytes are stable against lithium metal and stable against more energetic cathodes. Therefore, we can use these more energetic materials, so lithium metal, and using certain redox in cathodes. So one example is, instead of using cobalt, using nickel, where this distance you can go up to 4.5 volts between nickel 4 plus and nickel 2 plus. Manganese is another one. So you can start looking at some of these more energetic materials, more energetic cathodes, and lithium metal as an anode. And therefore, because you're getting more energy per electron, which goes around the circuit, and you don't actually affect the mass that much of the cell, you get longer vehicle range. And these will be the batteries of the future in about 10 to 15 years' time. This will be what will be used in these batteries. But at the moment, it's purely a research stage of trying to understand how things interact within these cells. So yeah, I also saw mentioned on the Slido earlier on polluting. There is work done in my group. I don't do it myself, where they're looking at using more abundant materials. So looking at sodium batteries, because sodium is much more readily available in the Earth's crust than lithium is, which is, for an ethical and polluting standpoint, much better. So yeah. Any other questions, Richard?
Thank you very much. But you've covered so much.
It's a lot. Just to add that some of that stuff is what you would do more in university level courses, and it's kind of giving you an up to speed of what research is actually being done on batteries now. So work I'm doing on these materials, you've kind of been given an introduction to it, which is 5 years further on than when you would be taught it.
That's great, though, Bart, and that's the essence, arguably, of supercurricular enrichment, because you're taking things beyond a level that you do within the syllabus in your own school. So thank you for that. We've had how many questions we've got? We've got 4 questions. So dealing with them in turn. When did you realise that you were interested in batteries? And what sparked it off? Is that somebody going for a bit of a pun there? I don't know. What sparked it off? When did you realise that you're interested in batteries, and what sparked it off?
So for me, it was second year of sixth form, when I had a really rubbish phone at the time. I think it was an iPhone 5. It was really bad. It was so many years old, and I was keeping this thing going. And it was the winter time, and I noticed that in the winter, or like when I was inside on my phone, the battery, while bad, it would last a decent amount of time. Whereas the moment I went outside and it was cooler, my battery would go really flat really quickly. And it was really bugging me that it would happen, because I'd go out to see some friends, whatnot. I'd think, based on me being in home, my battery should last me like 2-3 hours, and it would go flat really quickly. And I didn't understand why. But it's actually to do with this sort of thing. I went and did the research myself, and this energy here, this enthalpy, has a temperature dependence. So when it's cooler, you get a smaller voltage, and that causes your phone to die quicker. It's because you have a smaller voltage here. So there's a temperature dependence on this. And that's when I was first interested in batteries, because I was went and did some reading, found that out, and then I kind of found the world of trying to optimize this number, try and get larger batteries, more energetic batteries. And that's how I knew that was the beginning. And then it kind of learning about it at university, definitely I was like, this is the thing I prefer the most out of everything else in my course.
I love that you're interested in that. So hang on, this is my question, not our participants, but come back to their questions. So you then went and did chemistry, but then at that stage, second year of sixth form, you got this particular passion. With most degrees, you have to do loads of broad-based stuff first. Had you already at that point thought, when I do my chemistry degree, maybe later on, I'm going to try and specialize in some battery stuff, maybe in years 2, 3, 4, that sort of thing.
I would say it was more kind of like a passive thing in the back of my mind. Like I went to all of my courses. Well, in first year at Warwick, I know that we didn't have choice. Over my first 2 years, I didn't have choices over modules, but I did electrochemistry in both first year and second year, and those are the courses I preferred. And that kind of affirmed the curiosity I had when I was in that second year of sixth form. So when I was 17, turning 18, it affirmed that curiosity. And then when I got the option of choosing modules, I chose more electrochemical modules. And I did my fourth year master's project on synthesizing new battery materials or potential new battery materials. And it was then which I was kind of like, this is exactly what I want to do. And I want to do more research. And then I applied to do my PhD where I am now. So it was kind of like a small like nucleation of the idea when it happened was in sixth form, but it was going to university and doing all of my courses, which was kind of like, actually, yes, this is correct. That's what I find the most interesting.
And a typical journey there in terms of, doing a broad-based introduction in your degree and then specializing things later, which is what generally happens. Thank you for that.
Mm-hmm.
Are there any resources for sixth formers you'd recommend for students interested in chemistry? There's two similar questions here. The first one, then, for people interested in chemistry, anything you maybe enjoyed when you were sort of in sixth form?
The most I really did in sort of trying to further my my education myself was there was a book. I can't remember. I think I remember the title, which was Why Reactions Happen or Why Chemical Reactions Happen. And I got that when I was in sixth form. And that it was kind of like the step up from what you learn. And if you find chemistry really interesting, but you want to find out more reasons, like actually, why does this happen? Why does this happen? It definitely answered some of those questions which I had, which I felt weren't answered in the A-level course.
James Keeler, Why Chemical Reactions Happen.
Yes, that's exactly it. Actually, yeah, I know him because he does some NMR. I do a lot of NMR in my work, but yeah. It's weird now I know him and I've read his book when I was 18. But yeah,
it just happens to be an Oxford University Press book as well. It sounds like we're trying to push our own university here, isn't it? But doesn't it? But this is just a coincidence.
But it's really helpful as well for first year of university. So first year of university, what they aim is everyone's done different curriculums. They want to get everyone up to like a similar standpoint. And some of the stuff which he goes through in that book is basically first year university stuff, but it's pitched at just the right level that you can try and understand things. And that was also one of the things which helped make my decision, because I both loved physics and chemistry at sixth form, but it was reading that book and the kind of curiosity of the electrochemistry behind my phone where I was kind of like, yes, chemistry is it for me. So yeah.
Brilliant, thank you. And then a similar question, I suppose. Any books, podcasts you like for finding out more about batteries technology? Anything, again, more specifically about batteries? Perhaps something that's quite accessible or...
Yeah, this is the issue, is this is a completely separate issue with not academia, but things in literature in general is so inaccessible. Because I can already think of quite a few papers which would be perfect, but they're so inaccessible because they cost so much money to access. But in terms of books, no.
Is this a gap in the market then, Bart? Are you thinking, I might just write, the layperson's guide to batteries?
New Scientist might have done some stuff, but nothing I've read recently. Because I was kind of the way I learned all of this stuff was mainly from literally Googling when I was 18. And then once I got to university, you have your university log on and have access to the wide world of papers. So if you have a question, you can go to your literature database and find a paper with an answer. But yeah, Googling is the annoying answer is if you have like a burning question, Google. But if you're trying to find something which would give you insights into actually current research, I'm not too sure.
I'm sure magazines like New Scientist and
Yeah,
Nature
New
all have
Scientist.
all sorts of stuff because it's such a
Yeah.
topical area. And reflecting that topicality, the last question here, and please, if there are any more questions, do submit them now on the Q&A tab. Is the world ready, from what you're saying about batteries right now, for the introduction of electric cars that some governments are bringing in with laws? I think you might have implicitly given an opinion on this, but yeah.
So it's a very difficult question. A lot, as this person's mentioned, a lot of countries have said we're going to go. I think Norway might have been where we're going to go 100% electric vehicles by 2030. But the issue is there's no actual way of picking up the kind of energy costs which that will cause, if that makes sense. So at the moment, countries only produce X amount of energy, but if everyone had electricity, but if everyone had an electric vehicle and wanted to charge it at night, there isn't really the infrastructure for that, and they produce many more times than that number. They would require many more times than that number. So it's kind of an everything approach from multiple directions, where I'm looking at optimizing batteries to store more energy. But I know of people in this department who, not in this department, in other departments, chemistry has a few, where they're looking at ways of optimizing, say, solar cells and the way that they get energy, so they can get energy from parts of the visible spectrum which they haven't used before. And so it's a multi-direction approach from various different areas of research. So hopefully by the time it gets to, say, 2040 and 50, for when we've said 100% electric vehicles to be sold, or 100% electric vehicles, I think it's 2040, don't quote me on that, that we will be able to generate the amount of electricity renewably to cover the entire market of the electric vehicle sector.
And but by infrastructure, you mean us powering them at home? Actually, you're not talking about like Tesla stations on motorways and stuff. You're talking about us actually
having enough electricity. And it is an important one. And another thing is why this is going on more political tangent. It's why countries like France, where they have a lot more electricity produced by nuclear power, are much better, because you're limited with the amount of energy you can harvest from wind, solar, and hydrothermal, because it's dependent on the amount of energy the sun heats up the earth by every year. So you're kind of limited by that, by the total amount of energy you can get. So if you to cover the whole world in solar cells, you would get a certain amount of energy off of it. Whereas nuclear is an untapped resource, where it's not. Same with geothermal, where it's not dependent on that. So there are countries like France, I feel, in a stronger standpoint personally.
Thank you, and thanks for being willing to share the opinion there as well. But thanks so much for sharing such insight and such passion as well this evening, your particular area. This has been recorded as well, so I know people are going to be watching us retrospectively after the event. Thank you also to our live audience and the questions they submitted, which have been absolutely brilliant and greatly appreciated, and your participation in polls. So all that remains is for me to say thank you and goodbye, and Bart, I'll leave the last word for you.
Thank you everyone for turning up and asking all of the questions. I hope I have inspired you to do battery science in the future, and if not, just chemistry, physics, or any form of science. We need you.
Oh, lovely words on which to end. Cheerio.
Cheerio. Bye-bye.